This video is part of an online course on algebra and will be about basic logic. Mathematics deals with proving statements about mathematical objects. Mathematical objects are of various types. They could be simple ones like what you have studied in school, triangles and circles, numbers, sets, functions, even more complicated objects like sets of functions, manifolds, etc. A statement is an English sentence comprising words and symbols that assert something about a mathematical object. Let me give you three example sentences. The number 6 is an even number. Isaac Newton was the greatest scientist. 3 is the first prime number. Notice something peculiar about the second statement. It is a statement that asserts something about a real person who existed, namely Isaac Newton. In this course, we consider only those statements that assert something about a mathematical object. So, the second statement is not considered a statement in this course. The first statement, the number 6 is an even number, is an obviously true statement. The third statement, 3 is the first prime number, is an obviously false statement. In this course, we will denote mathematical statements by lowercase letters, typically P, Q and R. A mathematical statement's characteristic property is that it is either true or false. It is never both true and false, nor can a statement be neither true nor false. Neither of these two options are not available for us. Mathematical statements are also known as propositions. Given some basic mathematical statements, we can combine them to produce compound statements. There are 4 logical operators available to us that are commonly used to combine simple mathematical statements to produce complicated compound ones. The simplest logical operation is that of negation. The meaning of negation is exactly what the meaning is in everyday usage. The statement negation of P, which is read not P, is true if and only if P is false. I take this opportunity to recall once again that IFF is the lazy shorthand for if and only if. So, the negation of a statement is true if and only if the original statement happens to be false. The next logical operation is that of conjunction. The statement P and Q, which is read P and Q, is true if and only if both P and Q are simultaneously true. Again, the meaning is not that different from our everyday usage of the word and. The third logical operator is that of disjunction. The statement P or Q, written PVQ and read P or Q, is true if and only if at least one of P or Q is true. One crucial difference between mathematics and everyday usage of the word or is that in mathematics the word or is always used in the inclusive sense. That means the statement P or Q is true even if both P and Q are simultaneously true. Now, in the real world, depending on the context, the meaning of the word or changes. For instance, let us say you are visiting a 5-star hotel and there is a breakfast buffet and the waiter comes and says choice of beverage, coffee or orange juice. I think it will be pretty strange if you say I want both coffee and orange juice unless you are King Alfonso or someone very special. Typically there it is not inclusive or. On the other hand, suppose you have done some blood tests and you visit a doctor and the doctor says something like your sugar levels are marginally high. If either your father or mother have diabetes, then you have a very high chance of getting diabetes. Surely the doctor here means inclusive or. if both father and mother have diabetes, doesn't mean that suddenly I will be miraculously immune from getting diabetes. So, in the second sense, or is inclusive. So, in the real world, or is used sometimes in the inclusive sense, sometimes in the exclusive sense. We pick that up from context, but in mathematics everything has to be precisely defined, things cannot be left to be inferred from context. So, we always use or in the inclusive sense. If we want to say exclusive or, we will explicitly write P or Q, but not both, to make sure that the meaning is crystal clear. We now come to the final logical operator, that of implication. Like most scenarios, the last one is the most important one, and in this case not only is implication really important, it is subtle. The statement P implies Q, read P implies Q or if P then Q, is a subtle logical operator. I am going to tell you the only scenario under which P implies Q is false. The subtlety comes because in almost all situations P implies Q is true, only in one situation P implies Q is false. The statement P implies Q is false if and only if P is true but Q is false. In all other situations P implies Q is true. So, let me introduce some more terminology. The statement P is called the antecedent, whereas Q is known as the consequent. The subtlety of the implication can be brought out by considering what happens if the antecedent is false. From the way we have defined implication, when the antecedent P is false, the statement P implies Q is always true, irrespective of whether Q is true or false. So, imagine why we have defined implication this way. Let me give you an example. Suppose I make the statement, if it is raining, then I will carry an umbrella. Now, under what situation am I lying? What situation have I uttered an untruth? Let us think about that. If it is raining outside and I indeed happen to have an umbrella in my hand, then certainly I am not a liar. But on the other hand, consider what happens if it is not raining. Now, I have not made any assertion about my behavior when it is not raining. Maybe I like to carry an umbrella regardless of whether it is raining or not. Maybe I will not carry an umbrella if it is not raining. Maybe I am not committed either way. Irrespective of whether I carry an umbrella or not, when it is not raining, the statement if it is raining then I will carry an umbrella, it is irrelevant to the situation. That is, the statement if it is raining then I will carry an umbrella gives information only about my behavior when it is raining. Therefore, in all other situations we assume that the statement is true. This is by convention backed up by this heuristic examples of our everyday usage of the word implies. Okay? Now, implications that are true because the antecedent is false are known as vacuously true statements. That is, because the antecedent is false, it does not matter what the consequence is, P implies Q is true. Such situations are called vacuously true statements. I want to make one distinction between the daily usage of the word implies and the mathematical usage. In mathematics, no causal relationship is expressed by the statement P implies Q. For instance, I can say stuff like 2 is an even number implies 3 is a prime number. Now, 3 being prime has nothing to do with 2 being even, they are different things, but both P and Q in this case are true. Therefore, the implication 2 is even implies 3 is prime is a true statement. Whereas, in the real world we never make implications like this. Implications usually suggest that the antecedent in some way forces the consequent to be true. Now, I am not saying this is never the case in mathematics. More often than not, implications are true because something about the antecedent P forces the consequent to be true. But all I am claiming is that the precise definition of implication does not give you any information about causal implication between the statement P and Q. Keep that in mind. Back to the empty set. In a previous video, I asserted this somewhat innocuous claim that the empty set is a subset of any set. With the subtleties of implication now mastered, we can see a full proof of this fact. Suppose we want to show that the empty set is a subset of any given set A. What does that mean? If an element x is in the empty set, then x must also be in A. That is the meaning of empty set is a subset of A. So, when you write this as an implication, x in empty set implies x in A. Now, how can this implication be false? The only way by which this implication can be false is if the antecedent is true, whereas the consequence is false. But that can never happen because the antecedent is plainly false irrespective of what x is. By definition, the empty set is the set that has no elements, therefore, this antecedent can never be true. So, the implication is a vacuously true statement. Now, if we are given a compound statement, how do we determine the truth or falsity of such a compound statement? Well, the standard way to do it is to draw what is called a truth table. Now, I am fairly certain that a non-trivial amount of your life has gone in drawing such truth tables. So, I will not be elaborate, I will just give you an example of what a truth table is, and that should jog your memory, ring a bell, recall for you what truth tables are. So, here I have drawn an elaborate truth table for the very simple statement P and Q or P and R. So, what you have to do is you have to list out all possibilities for P, Q and R. There will be exactly 2 cube, which is equal to 8 possibilities. Best to list them in some order, either in increasing order or in decreasing order, whatever that means. So, I start with true, 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 false, so on and so forth. Then I have various constituents of this compound statement. I write out the corresponding truth values of P and Q and P and R based on the values of P and Q, and then combine them in the obvious way, and I have produced the truth table. So, please work this out for 5 minutes and forget about it, it is not very useful for this course, but it is good to know. So, in this particular compound operation, it is true under 3 scenarios, in the remaining 5 scenarios it is false. Now, we come to the important notion of a tautology. Now, I know that in rhetoric, speaking in tautologies is considered a bad thing, but here the meaning of tautology is somewhat different from the way it is used in rhetoric. Consider the compound statement P or negation P. Either by writing out the truth table, which is an overkill in this situation, or just by thinking about what the meaning of or is, you will come to realize that the statement P or negation P is true irrespective of the truth values of P. In some sense, the statement P or negation P is true because of the very nature of the logical operations. In other words, by the meaning of the word or and the meaning of the word negation, this statement turns out to be true. Such statements are called tautologies. So, in other words, tautologies are those statements irrespective of the truth values of the individual constituents, the compound statement is always true. Again, to check whether some particular compound statement is a tautology or not, the simplest, most straightforward and most brutal way to do it is to just elaborately write out the truth table and check that the last column consists only of all truths, then it will be a tautology. We now come to the important notion of a property. As we saw in the video on basic set theory, it is not possible to describe complicated sets just by listing out the elements. We need properties. What is a property? Well, you are given a set S, a property on the set X, on the set S is a sentence that involves a variable X. When you plug in a concrete element of the set S in the place of X, then P of X must become a proposition or a statement. That is, it must become a true or false claim when you substitute a particular element in the place of X. The best way to understand what it is to see an example. Look at the statement. P of X by definition is X is an even number. This is defined on the set natural numbers. This statement will be true precisely when X is 2, 4, 6, 8. When X is 3, 5, 7, 9, it will be a false statement. In other words, if you look at the collection of all X in the natural numbers such that P of X, what I mean by that is it is the set of all elements X in N for which P of X is true. So, this is a shortcut for saying consider the set of those elements X in N for which the property P holds. So, if you take this concrete property P of X, X is an even number, then this set is nothing but the set of even numbers. Okay? So, using properties we can define subsets of a given set. Now, notice by substituting an element in the set S in the place of the variable slot X, we can convert a property into a statement, true or false statement. There are two other ways to convert a property into a statement, that is by using quantifiers. These come in two flavors. The first one is called the universal quantifier, that is for all X P of X. I prefer to read this quantifier, which is written like an upside down A, as for each X P of X. Now, when is the universal quantifier, what does it do? Well, the statement for each X P of X is true precisely irrespective of which element X you substitute in the place of X. The resultant statement P of X is always true. The existential quantifier is in some sense a dual of the universal quantifier. You write it like a mirrored E, there exists X P of X. You can also read it as for some X P of X. The existential quantifier, what it does is the statement there exists X P of X is true if there is at least one choice of an element in S such that when you substitute that element in the place of X, P of X should be true. So, technically both terms universal and existential quantifiers, their meanings are sort of self explanatory. So, I have written out what it means in elaborate detail when for each X P of X is true, when for some X P of X is true. Now, I mentioned that this quantifier is read as for each by me, but it is usually read as for all. Now, the reason why I would like to read it as for each and why I recommend that you also read it as for each is that when you say for all X P of X, there is this misconception that you are substituting the whole set S altogether in the place of X. That does not even make sense. So, technically you can substitute only one by one. So, the terminology reading it as for each X seems to be more what you say congruent with the actual meaning of the universal quantifier, but it is up to you. And as you would have noticed already, since I am so used to reading it as for all from all the textbooks that I have read, I will use for each and for all, not really being conscious of which one. Okay. Now, we already saw the property of being even. Now that our vocabulary has been sufficiently enhanced, we can define what being even is in even more detail. Look at this new property E of X which is also a property defined on the natural numbers. It says for some y in n, x equal to 2y. Notice that the definition of E of x itself involves a quantifier, an existential quantifier to be precise. So, this is saying the even numbers are precisely those that are 2 times some other number, and as we know these clearly define being even. So, you can write out properties using set theoretic notation in great detail. Many of the commonly used properties can all be written using basic building blocks, using quantifiers, and the symbol there exists. Now, there is a deep reason why I am making this remark, but I will not elaborate. If you get a chance to read Naive Set Theory by Paul Halmos, you will sort of be able to figure out why I made this statement at this stage. Okay. Now, coming to an important skill that you must master. You must have already encountered in your studies in school that oftentimes you prove things by saying suppose not, or saying assume to reach a contradiction that something is false, and you do something and you get a contradiction. That involves negating complicated statements. Okay? Now, if your English language skills are exceptionally good, then just by understanding what the statement P of x is saying, you will be able to easily negate it, even if that P of x within itself has 17 quantifiers. Just by knowing what the meaning is, you will be able to negate it. But that is error prone. If you make one mistake in your understanding of the statement, you will be in error. I will give you 3 principles using which you can negate practically any statement, no matter how many quantifiers there is, no matter how complicated the statement is, the property is. Okay. So, let us look at negation for all x P of x. Well, the negation of this is nothing but there exists x negation P of x. Okay. Why is that? Well, let us think about this. For each x P of x is true, means that no matter what x I substitute, the statement P of x naught should be true. When will that statement for each x P of x be false? Only if for some particular choice of x, the statement P of x is false. In other words, the statement negation P of x is true, right. So, the statement negation for all x P of x is nothing but there exists x negation P of x. Think about what both statements are trying to assert in the lines of what I explained, and it will be crystal clear to you why the negation of this is this. In an exactly analogous way, the negation of the statement for some x P of x is for all x negation P of x. The reason why this is true is exactly analogous to the reason why 1 is true. Finally, double negation gets you back where you started. So, double negation S is the same as S, where S is any mathematical statement. Using these simple rules, you can negate any complicated statement. For instance, let us take the statement for each x there exists y P of x and Q of y. The negation of this is, well, first convert the for each to there exists and push the negation sign inside. Then again convert the there exists to for all and push the negation sign inside, and you will observe that within 30 seconds we have negated this. Let us look at it in English and do the negation in English. The statement for each x there exists y P of x and Q of y says the following: for each x there is a y such that P of x is true and Q of y is true. The negation is for some choice of x irrespective of the choice of y, the statement P of x and Q of y is false. Some of you might have instantly negated it using the meaning, but you should now at any rate compare how you negated mechanically and how you negate using the meaning, and see that both are actually congruent, both give you the same meaning. Now, the biggest subtlety with respect to quantifiers is that the order matters. We had this for each x there exists y, p of x and q of y. Suppose I change it slightly by swapping the quantifiers. Suppose I make it for some y for each x, p of x and q of y. The meaning completely changes. What is it saying? This new statement asserts that there is a single y irrespective of the choice of x. The statement p of x and q of y is true, right. This is very different from there being a suitable choice of y for each choice of x. Here you need a single y that works for every choice of x. So, the meaning changes. Because of these subtle issues that change the meaning just by swapping the order of quantifiers, because of these subtleties, it is better to mechanically do negations in the beginning. And once your facility improves, once you become strong, you will be able to negate virtually anything without errors, without any thought whatsoever. It is not that different from riding a bicycle. The first few times you will fall, but eventually you will learn that you will never fall. This is a course on algebra, and you have just watched the video on basic logic.